Hello, everyone. This is Tamil Selvan from Bharathasan University, India. I am going to present my research work entitled Numerical Simulation of Nonparaxial Solitons and Their Interaction Dynamics in Coupled Nonlinear Helmholtz Systems. This work has been carried out along with my collaborator Govind Rajan. These are my outline of the presentation, objectives, and introduction, and non-paraxial soliton and their interaction. Finally, we conclude with our remarks. Objectives. To examine the existence of non-paraxial solitons in a seamless system by using the standard Hirota's bilinearization method. Further, to investigate the scattering dynamics of two bright solitary waves by using the numerical scheme of the split-step Fourier method. Introduction. In general, the area of nonlinear optics deals with the consequence of the modification of the optical properties of a material system by the presence of light. To further elucidate, I have shown the generalized equation for polarization in terms of field strength E. The first term indicates linear polarization, which is dipole moment per unit volume. The second and third terms are attributed to the second and third harmonic generations. Notably, in 1973, Asiko and Tappert have been theoretically framed the nonlinear Schrodinger equation in order to explain the pulse propagation in optical fiber. Later, it has drawn a great attention in the area of nonlinear optics, in particular the formation of soliton. This is the mathematical form of the nonlinear Schrodinger equation. While deriving the nonlinear Schrodinger equation from Maxwell's equations, we treat the time as a slowly varying coordinate. So we ignore the second order derivative with respect to z because it is very, very less than the first order derivative term. Also, the standard NLS is acting as a fertile ground for many nonlinear waves, including optical solitons, periodic waves, pre-thirds, Vogue waves, and light bullets. Though the paraxial approximation has been extensively used to obtain many mathematical models supporting different nonlinear optical settings, including NLS-like equation. It is uh, failed to arrest the catastrophic collapse in higher dimensional systems as a consequence of losing the delicate balance between linear and nonlinear effects. It could be feasible to arrest the catastrophic collapse of high-dimensional NLS type systems either by applying higher order nonlinearities such as quintic and saturable nonlinearities, or by allowing the inherent non-paraxiality using the inherent non-paraxial term. It is possible to ensure the stable propagation of optical pulse even in the high dimensional NLS-like equation without altering the nonlinear profile. This is a nonlinear Helmholtz equation. Sorry, this is a nonlinear Helmholtz equation where kappa refers to the non-paraxial parameter, which is restricted greater than 0 in the framework of nonlinear Helmholtz equation, and gamma represents the nonlinear coefficient. In the physical setting of birefringent optical fiber, we consider the coupled version of nonlinear Helmholtz equation, which takes into account the crossways modulation. Now we enter into the main work of the presentation that deals with the formation of nonparaxial solitons. To obtain the nonparaxial solitons to the seamless system, we use the standard Hirota's bilinearization method. For that, we assume sigma is equal to 1 and we adopt the following rational solution form. That is, psi j is equal to g to the power of j divided by f, where g is the complex function and f is the real function. Substituting the rational form into the governing equation after some mathematical manipulation, one can obtain the one bright solitary wave solutions in terms of secant H form. Since in equation 9, one can find explicitly the phase and the velocity of the one bright solitary wave solutions. For the illustrative purpose, we plot the obtained solution 9, where the where one can get the same intensity profile for both the components as shown in figure 1a and 1b. Further, to elucidate the impact of nonparaxiality on the obtained bright solitary wave solution, we show the intensity and phase of the first and second components of the bright solitary waves as a function of nonparaxial parameter, where the amplitude of the both the component has increased, whereas the phase has decreased as increases in nonparaxial parameter. We then numerically study the collision dynamics of the bright solitary wave solutions of the CLS system by using the split-step Fourier method based on the Feitler algorithm. Here we use the analytical bright solitary wave solution as an initial condition, where phi is the phase difference, delta t is the separation distance. For phi is equal to 0, both the components demonstrate perfectly coherent dynamics of two bright solitons, where they display periodically repeated in-phase interaction that produce oscillating bound solitary wave solution. As the phase goes to pi by 2, it is repetitive nature of the periodic bound solution get drastically decreased almost 2 in both the components for the same length as in the previous case. The value of phase is then increased to the pi, which leads to the interactive nature of two solitons from coherent to perfect incoherent dynamics, where the two individual solitons propagates in a zigzag manner. All these plots are plotted for similar values of alpha and beta. It is possible to obtain the collision dynamics of asymmetric nonparaxial soliton by making distinct value of alpha and beta. Here it retains the same dynamics as in the previous case, except the distinct intensity profiles for first and second components. Conclusion. We have constructed one bright solitary waves for the seamless equation by using the standard Hirota's bilinearization method. Then we have examined the impact of nonparaxiality on the physical parameters, including speed and amplitude of the solitary waves discussed in great details. Following that, we have numerically demonstrated scattering dynamics of bright solitary waves, including two solitary waves, taking the obtained analytical solution as a seed solution by employing the split-step Fourier method. Thank you.